Yeah, okay, thank you.
Okay, I'm going to get started. Let's share the screen. Okay. Yes, you can see the screen, I presume. Um, so, how are you guys doing? Well, I presume. Yeah, especially for the project teams. Okay, so I hope you guys have been interacting with your teammate to thrash out some ideas that you may have. We will have some discussion about the project towards the end of the lecture, so please do stick around. The next assignment is almost ready. Okay, Madhukar has it almost ready. He's just applying the finishing touches. It will be uploaded tomorrow morning. And this is where you will be building a neural network to assist in playing the tic-tac-toe game and proving some properties about that system. So please look forward to an upload of that assignment on Moodle right tomorrow. So what I'm going to, so from now on, from here onwards for the next several lectures, we will be getting into under the hood of an SMT solver and look at some of the essential components of components that make an SMT solver, okay, that implement the different algorithms that interact with each other to solve the decision problem of formulas, quantifier-free formulas in SMT logic. So this, you've seen this picture before, but let me introduce this again. So these are some of the main solvers, okay? So as you know that an SMT logic is, the formula in an SMT logic is made up of atomic formulas drawn from several theories, a mixture of atomic formulas drawn from a mixture of these theories. And it can be any Boolean combinations of that, those atomic formulas drawn from various theories. The Boolean part, the Boolean superstructure of the thing is solved basically by a SAT solver, okay, a version of a SAT solver. And the SAT solver is the algorithm for SAT solver is called DPLL. That is what you will see today. And this in an SMT solver, the basic SAT solver, DPLL solver, is adapted. There is a T to interact with several theory solvers, and that's why there is this T in parentheses added to it. So we will both see DPLL, take a look into DPLL and DPLLT. And individual theories, there are separate solvers for each of the individual theories that an SMT solver supports. And these combination solving for combining these theories is done in another component called the core solver. Okay? And all these things interact with each other to make an SMT solver. So we'll first take a look at DPLL, starting with today and next lecture. Then I will introduce you to DPLLT and the core solver, and we will only at the end get into looking at a couple of theory solvers. For us, for this course and the application that we are focusing on, solvers for solving linear arithmetic is important, and an efficient version of it with the ReLU operator. So there are some special purpose theory solvers for linear arithmetic combined with ReLU, and that is also we'll take a look at. And if time permits, a couple of other solvers that might be of interest. Okay, so that is the overall plan for the next few lectures. So I'll begin by today talking about the basic Boolean satisfiability. A solver for Boolean, deciding Boolean satisfiability, propositional logic satisfiability. A SAT decision, a decision procedure problem for propositional logic is as follows. So given an arbitrary quantifier-free formula phi in propositional logic, check any one of the following. Either it is satisfiable. If it is satisfiable, produce a model, an instantiation for its variables, an evaluation for its the proposition variables, alpha. Or if it is not satisfiable, then proclaim it is unsatisfiable. So an arbitrary quantifier-free Boolean formula that can have any kind of Boolean operator. So here are some examples of some formulas where A, B, X, Y, and Z's are propositional variables. Now, propositional SAT checking is NP complete. That's a very paradigmatic and NP complete problem, but lots of other problems are NP completeness. So lots of other problems are proven by reducing it to Boolean satisfiability. Now, here in this course, we will not be concentrating on the complexity part and the hardness part of it, but every now and then I'll give you some indication of why these problems are hard and they are NP complete. So normal forms in any checking decision procedures, normal forms play an important role, because usually you get them, these decision procedures, they work on formulas by getting them, they check the satisfiability usually by getting them into one of these normal forms. And since these normal forms have some interesting properties and they're usually exploited, they are exploited in coming up with algorithms for deciding the formulas. So these are some well-known normal forms for propositional formulas. I presume you all know that they are, these normal forms are universal in the sense that they are general enough to represent any Boolean function. Okay. There's this conjunctive normal form. It's a product of Max terms. Okay, the conjunctions of clauses. I'm assuming that you all know this and how to get any arbitrary Boolean formula that have other operators into this form. And for our purposes, they are called clauses. It's a conjunction of clauses where every clause is a disjunction of literals. And a literal is either appears positively or negatively. A negative, I mean in negated form. Okay? So that is CNF form. So DNF is disjunctive normal form, where the formula is expressed as a sum of min terms, where a min term is a conjunction of literals. Oh, sorry, there is a mistake here. This is not a conjunction of clauses, but it's a disjunction of min terms. So where a min term is a conjunction of literals of this form. Now, both these normal forms are instances of a negation normal form. A negation normal form is one in which the negation operator appears only at the atomic level inside, at the leaves of the formula. For example, this formula that is shown here at the end is not in negation normal form. Why? formulas, getting formulas into negation normal form is interesting because they satisfy a monotonicity property that can be exploited in manipulating and deciding formulas. So what this, by this monotonicity property, what I mean is, so if a formula is in negated normal form, then if alpha is a model such that alpha satisfies formula phi, then if pos of alpha phi is a set of literals in phi that appear in positive fashion, that is not negated, in the model, then for every other model alpha prime where you so where the number, where the positive literals are more, okay, as long as you flip and then you any model which makes more variables go positive, make it go 1, they continue to satisfy that formula, okay? And it's fairly easy to check this, and that property is preserved only for when it is in negation normal form. There is another normal form that many of you might not have heard of. That is what is called, uses this operator called if then else. Okay, you've already seen that in SMT logic, at least in the SMT lib format, and that forms the basis of representing Boolean functions as binary decision diagrams. This ITE, formula, I'm not going to get into this today or not in this course, but if one is interested in doing BDDs use that form. And the ITE normal form is a canonical form, okay, unlike CNF and DNF, where there is a unique representation in this normal form for every Boolean function, which is not true for formulas in CNF and DNF, and that's why BDDs are quite interesting as compact representations for Boolean functions, and that can also be used for deciding Boolean logic. But SAT solvers typically use, not typically, always, almost all SAT solvers get the formulas into the conjunctive normal form before they do things on them to decide. Before I go into the DPLL algorithm itself, I want to point out for some easy cases, for deciding Boolean formulas. The satisfiability, if you have it in a DNF form, satisfiability can be checked in linear time, because DNF form is a summation, a conjunction of minterms. So where a minterm is a conjunction of literals. A conjunction of literals, a minterm is, for a formula in DNF to be satisfiable, one of its minterms should be SAT, must be SAT. It's enough if one of the minterms SAT, because it's a conjunction of minterms. And a minterm is satisfiable if and only if a variable occurs in it with unique polarity. You can't have A and not A kind of thing. So it's fairly easy. One pass through your formula will do that. Okay. So for example, here, this is unsatisfiable because A appears in both polarity. Okay. If it appears in one of the formulas, then it is unsat. Otherwise, if it is SAT. Okay, that's easy to check. Similarly, validity for CNF formula can be checked in linear time as well. Okay, in validity. Okay, whereas the validity of DNF is harder to check. Whereas for CNF, it is the validity that can be checked in linear time. That's because every clause, which is a disjunction of literals in the formula, it has to be valid. For a CNF formula to be valid, valid means that is true for all possible assignments to the literals. Then every clause in the formula has to be valid because it's a conjunction of clauses, and a clause is valid if it has one variable with both polarities, so that it'll become a tautology. Okay, in clause, for example, here both these clauses have at least one literal in with both polarity, and therefore it makes it valid tautologies, whereas this one is not valid. So validity is easily checkable. So why is then this problem so hard? NP.
Getting the terms into CNF or DNF itself.
Yeah. Say that again.
So given any term, getting a size of, getting an equivalent term that is in CNF or DNF and of a polynomial size is very hard.
That's right. So it's actually can be exponential, isn't it? Okay.
Yeah, it can.
Get them, we are interested in doing. So first of all, if you're only interested in satisfiability, you have a DNF form, this is true. But the way that I defined the Boolean satisfiability problem was for it to check both satisfiability and validity for arbitrary prepositional formulas. Okay, and therefore, and that's exactly the reason. To get them into one of these forms itself can have an exponential blow up. And that is why that is one kind of intuition for why it is hard. At least it's not as easy as these easy cases make them seem to be. So most SAT solvers, as I mentioned, the core engine by default works with CNF formulas in CNF form. So if so, then you can, from an engineering perspective, you can ask the question: if SAT solvers require before you can use them to get the things in CNF, isn't there a blow up already? Okay, because problems don't always occur. Most Boolean functions, cannot be compactly represented in CNF, or if you don't have, if the formula that you start out with is not exactly in CNF, they can be a blow up even before you use a SAT solver. Okay. So that's a real engineering question. Okay, so most SAT solvers use this encoding of arbitrary Boolean formulas. This encoding is credited due to one a person called Seitan, and that's why the encoding is called Seitan encoding. So in order to get, suppose you start with this. Normally you to get a formula that is not in CNF into a CNF form, you will be doing it by flattening, okay, by expanding out all these things. That if the negation appears not at the leaves, but at some non-atomic level, then you have to use De Morgan's law and distribute and over R and vice versa before you do it. And those are the rules, these distributive laws that cause explosion in the size of the formula. So the idea here is a compromise. Okay, you don't do that. You don't expand, for example. So any Boolean prepositional formula can be expressed as a network of gates. So these pointy ones are OR. This is the smooth one is an AND gate, and the one here at the output is a exclusive OR. So the idea is to not expand any of the Boolean operators. So you introduce extra variables, specifically a variable to not only for the primary inputs and the output, but rather also to all the intermediate the intermediate variables to represent the output of each Boolean operator. Okay, and then you express them, and you keep this operator and as is, and represent each individual operator, yeah, that the Boolean operator as CNF. Okay, so these are extra variables that I've introduced. So this Boolean function can then be represented as a conjunction of the value for all the outputs. Okay, and then you can assert that this to be satisfactory. Of course, this is not in CNF form. So then, for each of these, you could represent each of the operators as in CNF. Okay. So this way, okay. So this is, so there's an implication: X implies A and X implies C, and then for the output, and then A and C. Of course, you will have to have a CNF representation for every Boolean operator that occurs in the formula, and that's the idea. Okay, so of course, yeah. So you'll the CNF for each of the operators might have to be repeated several times in the formula, but you're not applying these distributive laws. These two formulas are not equivalent in the sense that, because one has more number of variables, but they're equally satisfiable, that whenever one is satisfiable, one is satisfiable if and only if the other is satisfiable as well. And yes, so the cited encoding has extra variables, and the number of extra variables that it induces is linear in the number of connectives in the formula. And it also, of course, since we have to convert each of the operator that appears in here, Boolean operator, into in CNF form, it also adds the number of clauses that it adds is also is linear in the number of connectives, the Boolean operators that appears. So this is the individual expansion for each of the Boolean operators in terms of relating the output of that operator to its input. Okay, and this is what you will add. So the important thing to notice is it's adding extra variables and adding these CNF forms for every instance of the connective, but it is not doing things. So there is a linear increase in the size based on the number of connectives. And almost all modern SAT solvers use this encoding before they encoding of the input formulas before they ship it into the core engine. Any questions so far? That's it. I'm going to skip. Yeah, I'm going to. Yeah, this is the title is kind of misleading, and this is I'm going to be using these examples to motivate what is called a resolution principle. Some of you might have heard of it. I don't know how many of you have heard of it. I don't know if your logic course, people who have taken the logic course. In the logic course, Praveen talks about resolution or not. But nonetheless, maybe even if some of you have done, because there are quite a few people who haven't seen resolution. This year, I'm going to motivate resolution. Resolution was one of the, resolution principle was the basis for one of the earliest decision procedures for propositional logic. Okay, and there's only a single inference rule that is enough to decide the all formulas in propositional logic. And this kind of also motivates why SAT is hard. Okay, so consider these examples. Okay. Okay, so first let me take this example. So this one, you can see it's easy to, okay, is it satisfiable? That's not hard to see if it's satisfiable or not. You shouldn't be spending that much time. See, this is satisfiable, and you can infer this very easily because every clause here has a literal that appears in with a unique literal that appears with a unique polarity in the entire formula. For example, A. So the first clause has A. Okay, that appears in with only one polarity in the entire formula. Now, B is B, whereas C appears with both polarity, okay? F appears with a single polarity, and so does E. So if every clause has at least one literal, yeah, then you can always make each of those clauses true, independent of without impacting the truth or falsity of any of the other clauses. Okay, so that is one of the easy cases, as a matter of fact, for deciding the thing, and that happens to be the case here. The checking becomes hard when you have something like this, okay? Because here, every clause has, a literal, there's no pure literals. A literal is called pure if it appears with only one polarity throughout the formula. Either it appears in a positive form or in the negative form. Okay, so that is not the case here. Okay, every clause here has a literal. No clause here has a pure literal. Every literal in every clause is impure in this thing, and therefore you need to. That is when you will have to start checking if one assignment to one of the variables interferes with the other variables. So so that's when the things start getting harder and trickier. So in this case, this formula is indeed unsatisfiable, okay? Because when you try to make B to be true, it is B not. You can't make this true, and then there is some circularity that can never be broken. And so is the case here as well. Okay, and that what gives rise to. So there are two ideas here. One is to point out the polarities when there are polarities of the literals that appear in the clauses are of opposing polarities, then they can be potentially conflicting. Therefore, in some cases, if like these, you may luck out and then have something like 5-1. Otherwise, you may have to look at all subsets of every possible subset of all clauses, and there are exponential number of them. So there might always be instance of that. That is also an intuition why this problem is NP. This also gives this searching and looking for literals with opposing polarities is a way uh, to actually use as a basis for checking if something is unsatisfiable or not. And the resolution principle is based on that observation that clauses, two different clauses, they can be potentially conflicting only if there are literals in them of opposing polarities. And that's what resolution principle is based on. So here is resolution principle attributed to Robinson, who introduced that in a paper in 1965. So if C1, let C1 and C2 be two non-empty clauses, so it means it has at least one literal, then and with C1 having a literal in positive form and C2 in a negative form, then the resolvent R of C1 and C2 on C is defined as follows. So as I said, so you resolve on this variable C, which occurs in opposing polarity in the two clauses. From that, you derive the resolvent, which by eliminating that the literal that appears in opposing polarity and taking the union of all the rest of the literals in the two clauses. Okay. And what it says is, resolution principle says is the conjunction of these two clauses above the horizontal line is satisfiable and only if the resolvent is satisfiable. And you have eliminated one conflict by doing this. And then it has two other things. At the base case, you have A and not A. If you have unit clauses, okay, with opposing literals, then of course that is a contradiction. And this is true, okay? If after resolving you end up getting B or not B, then it is true. B or not B is true. So Robinson's theorem was that C1 and C2 is equisatisfiable with R. Okay, I'm using the term equisatisfiable because they are not equivalent in that R has can have one fewer variables. Okay, and this is easy to see why, because if C1 and C2 is satisfiable, then maybe say the satisfying instance makes C to be 1. Then obviously, suppose this is satisfiable. If the satisfying instance is, assigns 1 to C, then this is this clause, the first clause C1 is trivially true. And in order to satisfy C2, you have to make one of the other literals in C2 to be true, because C bar reduces to 0 in this clause. So if one of the other literals in C2 is true, so is the resolvent. Okay. And the reverse also is true, because if this R is satisfiable, then one of these literals have to be satisfiable. If it's a B literal, then that makes R satisfiable. Then you can actually pick C appropriately. Okay, to make the other one, so C1 satisfiable and vice versa. And that's why this is easy to see. And the decision procedure, the earliest decision procedure that used Robinson's resolution principle as a complete decision procedure for deciding propositional logic, that's attributed to Davis Putnam. Okay, and it's actually called the DP in the DPLL stands for Davis and Putnam. So that's called the DP strategy, which uses resolution. And it is quite simple. So given a CNF formula phi, you repeatedly apply the resolution principle until you either derive a contradiction. Okay. And by the way, this resolvent is sometimes called an implied clause, because strictly C1 and C2 implies R. Okay. In this as a result of resolve. C1 and C2 implies R. So you either derive contradiction, or there are no new implied clauses that are generated. Okay. So yeah, if you're able to derive a contradiction, it is unsatisfiable. And then if you exhaust by deriving all, you can't apply resolution anymore, then you can say it is satisfiable. So that's DP decision procedure, the earliest decision procedures. Any questions? Okay. Yeah. So so there are a few things. So how does a resolution proof looks? Okay, resolution proof, as the procedure indicates, it's a sequence of sequence of applications of the resolution inference rule. Okay, until you get to one of these two kinds of things. So let's see with this. I have three examples to illustrate three things, and a proof is sometimes called a resolution graph. Okay, so for example, for the first one, phi 1, the resolution graph or resolution proof is what as shown in this picture. Okay, so you can derive a contradiction. Oh, this is for phi 2. I'm sorry, not for phi 1. For the formula phi 2, which is unsatisfiable, phi 1 is trivially satisfiable. So you're resolving the first two clauses on the variable b to derive a, right? If you resolve b, that which appears in opposite polarity, then when you take the union of the remaining literals, you get a. Similarly, if you resolve on c the other two clauses, you get a bar, and that and thereby you're deriving a contradiction. Okay, so this is what is called a proof as per resolution. Of course, there is no unique proof. There can be several resolution proofs for the same formula, and some of them can be very big and some of them can be short. This is what you see on the left side is one of the shortest proofs. So it entirely depends on which clause and which variable that you choose to resolve on. Usually the variable that you choose to resolve is sometimes called a pivot variable. Okay, so the pivot variables are shown with an arc here. Okay, in the pictures. Now let's concentrate on the right side, right-hand picture. So it's the same. So it's another proof of the thing where I've chosen to do some redundant resolution on some other clauses, in which case this illustrates two things. One is that there can be several things. There can be multiple resolution proofs for the same formula to show the contradiction. And there's also that you will need to, when you do this resolution, it's not just only on the clauses that appear in the original formula. So you will have to keep the new clauses as well. I mean, the resolution could be between the new clauses. It's not always only on the new clauses. You might have to do, you need to do the resolution on the original, between one of the new clauses and the original clauses. So you have to keep all the original clauses in addition to the new clauses. The proof on the left side so happens where you were doing you were able to get a contradiction by just resolving on the new clauses. So in general, that is not possible. You have to keep both of them. Okay, and that is actually the problem with this DPP strategy. It's very memory intensive, that it is several issues with this strategies. We'll get to that. But before that, when we are looking at proofs, there's another concept that I want to introduce, which is very important in Boolean satisfiability. This is called unsat cores. Okay, so let me introduce that by looking at a proof of the third formula, phi 1a here. So here is a proof on the left side. Okay, yeah, you can stop me anytime if I'm going too fast or a thing. I mean, yeah, so please do stop me if you have any doubts. So this phi 1a is not satisfiable. Okay, and here's is a resolution graph showing. So there are subsets of these formulas, some of which are satisfiable and some of which are not satisfiable. Okay, and the proof actually reveals that. You see that the unsatisfiability of this formula is shown by this small resolution resolution graph of this whole thing. Okay, and that's because this subset that I have included in the brackets is a subset. It's subset in terms of a subset of the clauses in the original formula that itself is unsatisfiable. Such subsets, a subset of clauses of a formula that is unsatisfiable, which itself, the subset itself is unsatisfiable, is called an unsat core, because that gives an essence of why the original formula is unsatisfiable. Okay, so for the yes, okay, and then you could get that by searching through the search from the resolution graphs. Okay, so in the fourth formula that I've shown here, there are two unsat cores. Okay, one that occurs between the squiggly brackets. Okay, the set of clauses that appear between these curly brackets, and the one that appears between square brackets, both of which are unsat cores because they are subsets of the original formula, which are themselves unsatisfiable, and therefore they make the original formula also unsatisfiable. So unsat core of an unsatisfiable formula is a subset of clauses of phi that is still unsat. Okay, but not any smaller. But any smaller set is makes it satisfiable. So it is the smallest. It is the minimal set of clauses. I've been using the word small. I mean, it should better to use minimal. Okay, and a minimum unsat core is called a minimum unsat core. A minimum unsat core is the smallest among the set, and there can be several of such things. Okay, so this you could do by techniques to extract these things from like I've shown here in resolution graphs, or even some SAT solvers. They give you these unsat cores, even if not the minimum one. Some unsat cores you can, and Z3 can actually do this. So as I was mentioning this Davis-Putnam strategy is very memory intensive for the primary reason that you need to keep all the new and the old clauses. There's also an issue of how you extract models from that resolution graph that I've shown, but that is not the thing. But the biggest problem is that it's not very goal directed. What order do you, what variables you use in resolution, what clauses that you pick to resolve, to apply the resolution inference greatly impacts the length of the proof that you can get. One technique that has that was tried later, and that's what is used in the next version of the procedure that I'll introduce you to, called the DPLL procedure. It biases the resolution towards unit clauses. Okay, unit clause is one which has a single a single literal. So we can bias your resolution towards either unit clauses or even short clauses, and hopefully, if you can get proofs using those, then you're done. And if not, then you consider the bigger clauses later. Okay. So, but that is kind of the idea behind the next version of the decision procedure, which is very important that you understand, because even to this day, state-of-the-art modern SAT solvers, they only use this DPLL procedure. Of course, there are a lot of techniques, additional techniques, some of which are techniques and some of which are heuristics, are put in, and a lot of engineering go into these SAT solvers to make them as efficient as they are in practice. But at the core, it is DPLL with a few breakthrough ideas, which we will get to in the next class as advances that most modern SAT solvers have, these breakthrough ideas. But today, I will introduce you to the basic form of DPLL strategy. It employs repeated unit resolution. A unit resolution is one. Yeah, I have a slide here. Okay, and it uses so it uses something called Boolean constraint propagation. It does by using Boolean constraint propagation. That's what it's called in DPLL, but it's basically unit resolution. Okay, a unit resolution is one where one of the clauses is a unit clause. Okay, it has two forms. If you have a unit clause, with which has a literal with opposing polarity with another clause, that's when you can apply resolution. So then, that becomes bottom. So you pick a unit clause to first resolve on. Okay, and if that, but the unit resolution also has this principle. So if that appears as if this P true and the P is true, if there is a unit resolution, a unit clause in your formula with and there's another clause which appears in the same polarity, then you can immediately reduce that to true as well. Okay, so both of these things, okay, what appears on the left side is actually resolution, and what appears on the left side you can call as simplification. Okay, and these two are what are applied. Application of these two rules repeatedly until you cannot apply it anymore is what is called, consists of involved in BCP, Boolean constraint propagation. Okay, the way to look at it is, you could just plug in the valuation implied by unit literals, unit clauses, and then you plug it in and then you simplify. Okay, so DPLL procedure is so it's biasing towards it's repeated unit clause unit clause propagation is what it is used. Okay, so you start with, first take the original set of clauses, the original formula containing a set of clauses. When I keep saying set of clauses, CNF means a set of clauses, means a conjunction of those clauses. Okay, and then you do BCP. If as a result of doing the BCP it reduces to true, then you can it as well. It is satisfiable. You're done. If as a result of doing BCP it returns false, then you return false. That is quite possible that as a result of BCP, maybe some of the clauses may get simplified to either true. If it simplifies to false, it's false. So some of the clauses may simplify to true, but there could be some clauses which still neither simplify to true or false. Okay. In that case, you will have to, only in that case, you start, in that case, what you do is you choose a variable. Okay. In the first phase, you're just propagating existing unit clauses through the formula. After you're done with it, if there's still, there is no definitive answer, then you do, you choose a variable with either the
Sir, what
positive.
exactly BCP is doing?
What?
What exactly is BCP doing?
BCP is applying these two rules repeatedly. So if in the original formula, there is a unit clause
No.
which is appears in negative polarity, then that variable has to be assigned a 0, okay, in order for the formula to be true. So in that case, it assigns it a 0 and then simplifies all the rest of the clauses. That's what it does. So if the original formula had a pair of clauses where one of them is unit, okay, P hat, and the other is a clause that has P in it, okay? So because a conjunction of this can be satisfiable only if P is set to 0, correct? Therefore, so any satisfying instance of this conjunction of these two things has to set P to 0. Therefore, it is plugging, in engineering terms, I mean, in simplified terms, it is plugging 0 to, that literal in the other clause and simplifying it. So once you get a false here, this one becomes a smaller clause with P gone, okay? If that unit clause in the original, unit clause in the original formula appears, is a literal in positive form, then you have to make that to be true. And then you plug in true to all the clauses in which it appears in positive form. And then you simplify that to true. Okay? So as a result of which, sometimes all the clauses may get to simplify to true, in which case you get a true answer here. But because there are other literals in the other clauses, the Boolean propagation is not necessarily, in all cases, will simplify all of them, all the clauses to either true or false. That's what BCP is doing. Just looking at unit clauses and then, assigning appropriate things and then using that to simplify the other clauses. Now, at the end of that, so you might still have, then you're forced to choose an assignment to a variable, okay? So when you're done with this and you still have not received true or false, what that means is that you end up having, okay, maybe, yeah. So yes, yeah. I think this slide will give that. So at the end of this BCP, I dwelt too long on the previous slide. So so at the end of BCP, now I hope you understand what BCP is. It's just looking at the unit clauses in the thing and then plugging the appropriate values to make them true in the rest of the clauses. At the end of it, if it doesn't simplify to true or false, the remaining clauses, obviously, there are no more unit clauses in the original formula. And so when you do this BCP, some of them get simplified to true. They are called satisfied, okay, and they disappear, okay? And some of them can get reduced to false, okay? And that is usually called a conflicting clause, okay? And then if any of the clauses simplify to false, then you're done, because the entire formula reduces to false because it's a conjunction. It is the third outcome in which you have to choose a variable. If it's unresolved, it can be, all the clauses can be unresolved. That is, they are not, your unsimplified non-unit clauses, okay? Because as I said, BCP is the repeated applications of this propagation, because as a result of one step of BCP, some of them are reduced to unit clause, in which case you will have to repeat that, okay? That's why I said BCP consists of repeated applications of those rules, okay? So, yeah, so there is one, yeah, as a result of BCP, which is repeated thing, you may eventually end up in all the clauses being unresolved, okay? That means they are neither simplified to, to true or false, or they don't even simplify to unit clause, which means they'll all be clauses with more than one literal, okay? In which case you don't know. I mean, whether that is, you still have to do more work in order to get a satisfying assignment. That's when what DPLL does is, what DP would have done is it would have used resolution, which is more like a proof, a deriving proof. This is more like a algorithm for deriving satisfying assignments. There, what it says is, it says, oh, you arbitrarily, forcefully choose a valuation for that variable, okay? Since you don't know, whether that will be a satisfying assignment or unsatisfying assignment, you're taking a risk, yes, okay? So then what you do is, you have to explore both branches. A branch where you choose P, where you choose one value, true for P, and that's what you do. So you recursively call DPLL by adding the unit clause P to the simplified G. The G is the simplified form of F after doing BCP. Okay? So this is equivalent to saying that I have decided to make P to be true. Okay? So if that gets a true result, then you're done. So if but if that also if it gets a false false result, you still have to explore the other branch of P being assigned 0. Okay, that's why there is a backtracking that you will have to do, okay, here, because you're forcing a decision on P which you don't know, whose outcome you're not clear about. Okay, this recursive invocation we'll call BCP again. Okay, so that's why this is like exploring the branch with P being assigned true. See if you can get a result there. If not, then you will have to get something on this thing as well. So yeah, and before I do it, let me take an example. Okay, so I have it so I think it'll be better if I illustrate it. That is a recursive style of doing it. So maybe yeah. So here is the same DPLL algorithm assigned as, so by the way, so the material that I'm, for my slides are, okay, this topic is, this subject is this topic that I'm covering here is the subject of chapter 2 in the decision procedure book by Cronin et al. Okay, so I'm using stuff from there, but I'm also adding a little bit of my own stuff and then drawing from other things. But the core of it is chapter 2 of the decision procedure book. So this particular diagram is derived from there. Okay, so that recursive procedure is exactly shown here. Okay, for a moment, ignore this analyze conflict. What you do is you should be starting with a BCP. Okay, the original formula, you run BCP on it. And then if there's no conflict at all, then no conflict means if none of the, the BCP, then if there's no conflict, then you go check, okay? If it reduces to true, then there's nothing more to decide. Decide here means that you're explicitly choosing to have. This initial arrow here should not be here. So consider that it is here. So because you're starting with the BCP on the original formula, as a result of which it may get simplified to true or false, in which case you're done, okay? You have the full assignment, you can go, at least the full assignment for those variables that you care for, and then you're to have satisfied, result satisfied. But if it still has unresolved clauses, I mean clauses that don't simplify to true or false as a result of BCP, then you make a explicit decision. Okay? Then if you get a conflict, then that is no longer a definitive conflict, okay? Because it is a decision, you have to explore the other side. That's when you backtrack, okay? The backtracking is in the recursive thing was you have to flip the decision in the latest the latest decision that you have made in the recursion stack, and that you do, and then until you have kind of explored all possibility, and then you backtrack. You end up backtracking all the way to the root. Then you can say it is unsat. Okay, and that's what is done. So let me take an example, and so ignore the title here. We only concentrate on this example in here. So these are the set of clauses. I'm going to be illustrating the working of the DPLL procedure on these set of clauses. The prime here means not. Okay? A prime on a particular variable means it's a bar. Okay, a plus is or, and these are the set of clauses. So the original formula is a conjunction of these things. So here, you see there are no unit clauses to begin with anyway, okay? So there's no use for the initial BCP propagation. So you're forced to make a explicit decision on a variable, creating forcing, adding a unit clause, okay? So that's a forced decision. Therefore, if you get a conflict on that, that doesn't necessarily mean that the original formula is unsatisfiable. It's only after you've looked at the other decision that you can conclude that it is unsatisfiable after flipping the thing. So yeah, so this means x1 is equal to 0. So now you do BCP. So the decision you made was making x1 to be 0. So you have so these three clauses, the only clause that where x1 appears, they get simplified. See, as a result of this simplification, there is the first clause becomes unit x4. So the BCP recursively propagates, that. Yeah. So ignore the animation on the left side here because that's building some graph that we will use later on. Okay. So what I have in here in this gray box, the x4 is equal to 1 is a implied decision as a result of, because this becomes unit, right? The first clause, and therefore x4 has to be made 1 in order to make this to be true. So that you get as a result of BCP. After you make a decision, you're doing BCP again. Okay, so that is what happens. So now, yeah. So after that, this thing is gone. Okay, so you still have the remaining unresolved clauses. So you now have to make a decision. So you do say I make a decision x3 is equal to 1. Then I'm exploring this part of the search tree. Okay, so this is pretty much a binary search tree. Okay, so when I make x3 to go to 1, after that I apply a BCP. So the BCP simplifies these two clauses in which x3 variable appears in some literal. So the second clause becomes unit. So BCP forces a decision on that. X8 becomes 0. So the first two clauses are gone. I mean, as a result of X8, there is another, the third clause also becomes unit, and that this propagation, BCP propagation, continues to do that. repeatedly. Okay, that's why X12 is forced to become 1. Okay. Yeah, after that, yeah, the things that are shown in red here are all gone, simplified. Okay, so now you are left with a bunch of unresolved clauses. So you will have to make a decision again. A decision again on the variables that are remaining in the unresolved. A decision on one of the variables remaining in the unresolved. So you do say you make a decision x2 is equal to 0. So that will force x11, the BCP will force x11 to become 1 because that becomes, that clause becomes unit. And after that, you're still left with 4 clauses. Then you say you pick x7 to do a voluntary decision on. And then there's x9 becomes an implied thing. Yeah, I ignore the 1 here. I don't know what 1 meant. Okay, so then you get a conflict. Okay, as a result of x7, x9 becomes 0. You see, I mean here. Oh, what I meant here was you can make x9 become 0, but that clause simplifies to 1. But x9 becoming, this clause becomes 0, but x9 becoming 1 will not make, will result in a conflict in the clause x7 prime plus x3 prime and x9. Okay. So as a result of making this voluntary decision, explicit decision of x1 becoming 0, 0 and this was x3 and x2 being 0, and all the other resulting implied assignments to other variables implied by BCP, you are getting a conflict. Okay? It's when that conflict arises, then you will have to backtrack. And the basic DPLL always uses backtracking to the most, the earliest or the latest decision point. Okay, so it would backtrack here and explode it here in this part, in the red dotted part of the thing, until either it gets a satisfying decision, which is done by all the things simplified to true, or with every decision results in a conflict. Okay, in which case, because you have explored both sides of this branch, you would then backtrack one level even higher up. Okay, so DPLL has to use backtracking in order to get a thing. At any particular moment, you have a set of partial assignments. In this case, before you got this conflict, you had a partial assignment of x1 0, x3 1, x2 0, and x7 1. That is a partial assignment. All the other assignments here are implied assignments. There you got a conflict, and therefore, so you always, at any particular point, you always have a partial assignment. If that partial assignment in itself, as a result of BCP, makes it true, then you have a satisfying assignment. If not, you have to backtrack, one level at a time until you have explored all the possibilities here. If nothing, then you will have to explore, backtrack one level higher up and then explore the unexplored branches of the tree. And that's how DPLL LL works. Okay. Yes. Now, yes. Any questions? Okay. So let me go back to the Yeah, so maybe I'll do this one. See, this is one of the disadvantages. Okay, one of the disadvantages. You know, for a very long time, DPLL was the basis for doing it. Very long time. I mean, there was another slide where I had this chronology of time. I think as late as maybe late 1980s, before you know, these one of the first breakthroughs came, which is what is called conflict-driven learning. There was some yeah. So until that time, DPLL was the thing. So the one big disadvantage of this thing is, of DPLL is illustrated here in this graph. Okay. Suppose you make certain decisions, voluntary decisions for the variables x1, x2, x3, x4, and then x5. All these decisions are explicit decisions, and you get a conflict. Now, that conflict might be because of x3 being because of the you know, the wrong decision that you made on x3. Okay. Then what will happen is here, because you're only backtracking one level at a time. That is one of the reasons. What you will do is, you know, you will be you will be encountering the same conflict that you that occurred here, okay, here as well. Maybe that conflict is dependent on the decisions that you had made earlier, okay. So therefore, that will keep getting repeated here, okay, where that is one. So which means that you're not learning anything from the conflict. If you learn it is possible to learn some clauses which kind of give the root cause of what caused the conflict, okay? And then if you add that conflict, if you add that root cause, which itself is expressed like a thing, then you can avoid repeating those things. You can avoid encountering getting those conflicts again. The other thing is maybe that even after that, maybe the only satisfying solution is here in the right side of x3 branch. Okay, so I mean, while it is nice to backtrack one level at a time, after you explore all possible combinations below that level, which kind of guarantees you the termination of this proof search. But what if the only solution, there is no solution at all, the solution is here? Then maybe you could win by actually backtracking not one at a time, and kind of jump to you know, to higher levels, and then explore proactively the branch. Okay, so those were the two things, two ideas that. Yeah, I'll go back to this slide. Yeah. So the main drawbacks of this approach, there's no learning. It throws away all effort invested in finding a conflict. And if you could somehow root cause that conflict and then remember something that may prevent that, that is one. And then there is non-chronological backtracking. You skip levels, okay, based on certain heuristics. That this is very much tied to this learning from conflict, okay, and that there is a very it's a criteria to indicate what level to backtrack to. So number one bullet, number two bullet, okay, those were the first two big breakthrough that came, I think, in maybe late 80s or early 90s, okay, that created, gave one order of, if not, one order of speed up, for SAT solvers. The second decision was a decision heuristics, picking which variables that you want to decide on. Okay, that gave another. Both of them gave several orders of magnitude. So among all the other engineerings, these techniques, these are the two that gave the biggest breakthroughs, and that's what we will be covering in the next class. Okay, so yeah, I want to stop here and entertain any questions that you may have. Any questions?
Sir, you haven't uploaded the Hitar's Z3 code.
Oh, he still has not done it, is it? Okay, so I will do it. Okay. Uh, is this, who's this? Who asked this question?
Kapil.
Okay, so I will remind him again. Okay. I will remind him again, so you can also send him an email. Yeah, I will remind him again. Okay. Okay, so if there are no
I wanted
further
to ask,
questions, yeah.
whether there was. I wanted to ask whether there is a quiz on 15th for model check-in course.
Well, I had not announced anything officially, but now that you mentioned in your email, that gives me idea. Okay, I'll have to schedule it at some point, and I will think about it and I will announce it. Yeah.
Okay, so
That's
basically,
a, this
it
question is
was
not
listed in
relevant
the
here.
class schedule, or I
No,
mean,
no,
the coursework. Yeah,
I want to preempt
but
this
it wasn't in.
question. Okay, this question because this is SMT class, so let's keep this.
Okay, okay.
Because this question may not be is not relevant for several people here. Yeah. Okay. Yeah, but the simple answer is I'll make a decision on that. Yeah, but that is not decided yet. I mean, the only reason yeah, I don't want to say any further than that here. So let's stick to the subject matter. Any other questions? Okay. So yeah, so I want to spend maybe 5-10 minutes to see if you guys have had any time, had a chance to think about the problem that you want to solve for for designing and verification as part of the project. I would, I know that yeah, so we will also be making some effort, but I want you, I mean, I was hoping that you guys can do some Google search. Google is a wonderful thing. You have ideas and you can come up with ideas. Okay, so I don't want to discuss. So I mean, I asked a question, you have to answer. So I guess there's no answer. I'll say that either you have not spent the time on discussing with your teammate, or even after discussing, you've not been able to come up with an idea. Okay, so I would want you to, between now before the next class, make do some search. Okay, what could be the nice problems, and so on, so that can be solved, and think big to begin with. Okay, I'd rather say that you think big. Then we could tone it down. Yeah.
I had an idea, but I don't know whether it's interesting enough or not.
Correct. Okay, now that's good. That's good progress. I don't want to discuss the ideas here. What I want you to do is just make a one para description of the idea. Email it to me, Madhukar, and Hitar. Okay, we can discuss that. Then we can have some individual interactions. Okay, So with you and your team and your teammate, and that's the one that I want you to do. I want you to take some proactive step in coming up with some ideas, because that's part of this thing. I know that maybe some of you are more of an expert on neural network. I would be surprised than me, certainly, or any of the things. I know what neural network is and what it is to be done to model it, and so on and so forth. Okay, to really think of, yeah, so we can pick, maybe you guys can help in doing that. If you really do have ideas, I want to encourage that. Okay, and then we'll jointly decide. What we can give you guidance also is on whether Hitat has some experience in designing, and then how what is feasible to design, and so on. Maybe you can't, but certainly from the point of view of verification, this is too big, or where you want to cut it down to size, there, we will discuss and help. At least for ideas for doing things, it'll be nice if you can come up with it. And I don't want to discuss it today, but I want you to seriously engage the next 2 days to discuss with your partner, and then try to come up with that. And if after that you are still unsuccessful and have no clue, then we will do something. Will help you out. Okay, so that I certainly am hoping that you will do between now and Friday. Can I count on you to do that? Or you would at least say, well, look, I mean, I'm not getting it because I need this, okay? Where can I look at, okay? Give us some, ask us some questions. What might be the thing, So I want you to be proactive, and I don't want everything to be assigned to you, okay? And do it, which eventually we will do. So far we have not come up with that list. We are working on that list. But before that, it'll be nice if you can take some initiative. Yeah, that's what
I have some ideas, but I don't think they're quite concrete enough for me to.
Yeah, but then you don't have to
be
think.
Discussing and
Even
thinking.
our idea, yeah. So is it good enough? If it's good enough for discussion, even if it is, don't be shy of doing it. Make a description out of it, and if you have it on paper, not for making it as a definitive thing. I think putting down on paper will help you clarify those ideas, even when you want to explain it to people. Okay.
Right. Yeah. I will give it some, like, maybe a few more hours or something of thought, and then I'll maybe.
Okay. That I want you to do. Yeah. Okay. So that's what I wanted to add. I wanted to say, Madhukar, do you have anything to add? I don't see Hitat today. But,
yeah, I don't have much to add except that the description which you are asking them to send. So once we circulate the assignment tomorrow morning, they can understand how. So this assignment that we are circulating tomorrow morning is also a similar exercise, except that it is at a much a smaller scale, and we are only trying to verify a couple of properties. But at least it will tell you how you can think of a network, and how you can imagine the task of constructing it, training it, and then defining some properties which you can verify. So this is something that we have discussed and we have constructed on ourselves, starting with the idea. So a similar exercise has to be done. So perhaps when you read the assignment problem, you will get some idea.
I think that's a good point. So that will give you some idea. So it's that is a problem that Madhukar made up and constructed, and it is something which is much more complex than the toy problem. Maybe not. Maybe I don't know if it is comparable to what Hitarth showed in terms of the digit recognition. Okay. Yeah, but it is. It gives you some idea. So what you want to do is to scale that thing up. Okay. To, like we said, we want, in order to try these challenge the SMT solver, it has to be the scale. So we want that to be beyond that scale where it will come. And then the problem should be easy enough for you to suitably define a DNN, which will mean that maybe the inputs, etc., the problem has to be appropriate. And yeah, and the network at the top, and the problem should have some interesting properties, okay? Both safety as well as things. So for example, collision avoidance, that is, it has very interesting properties, okay? Maybe image recognition applied to some particular kind of application could be one idea, where, you know, other thing is, it has to have interesting properties. Besides correctness properties, you may also want, if it can also entertain some perturbation properties, then it will be good. Okay, it will make it even more interesting. And yeah, so in all these things as far as the application is concerned. But if you have a completely different idea, so then that's, you know, all the more reason that you have to propose it as quickly as possible, and so that we can finalize what it is. Okay, so maybe by the end of the week, you know, we'll have maybe some guidelines and some list of things on our own. Okay, but the reason I'm waiting to publish that is because I also want you to put in some effort to brainstorm with your teammate and then come up with some ideas. Okay, even if they are wild ones, you know, we are willing to listen. Okay, so please do spend some time on it. So we will discuss it between us, okay, individually, outside of the class. Okay, thank you.